So good morning and welcome to another Chai. I hope everybody is awake. And sorry for a little delay. We are late because of some small changes at the venue and some bedsheet arrangements that we had. So all good, and I'm very happy to introduce today's speaker, Dr. Joe Ninan. Joe joined TIFR as a faculty in Department of Astronomy and Astrophysics just a couple of years ago. But before that, he joined TIFR in 2010 as a research scholar. And then he has been actually with outreach, maybe also with outreach. And today he's going to talk about exoplanets. Yes.
Thank you. Let me share my screen here. All right. Okay. Thanks a lot for coming. Really great to be back. I think last time I gave a chai and talk was 7-8 years ago. So it's really nice, to be back here again and talk to you about how to evaporate exoplanets. So before we go into evaporate atmospheres and things of exoplanet, just to bring everybody to the same page, I will also give you a brief introduction about how we actually detect them, how we understand these systems, how we discover these and all these kind of things. So this question, are we alone? Right? This has been a question which has popped up in people's mind at some point of your life, right? Are we the only civilization in this universe? The universe is so big. Could there be other civilizations like us out there? And it's not just us who have been thinking. We have been thinking about this problem for really long time. We don't know when human started thinking such questions, but the written proofs goes back to like 300 BC. Really long ago, when humans were literally made of marble stones. Epicurus, he has written about the possibility that there are infinite worlds just like us and unlike ours out there. And we must believe that all of these worlds contain living creatures, plants, and other things that can see the world. Right? So it's been like for more than 2,000 years, humans have been postulating that our universe might be full of worlds just like ours. This became really popular during the Renaissance time, especially in Europe side. Two famous philosophers talked about there would be countless suns and countless earth, all rotating around the sun, just like our planets are going around the sun. These planets might be going around the stars. And they can have this n number of planets with countless worlds in the universe, no worlds, and no one less inhabited than Earth. It's interesting that he mentioned exactly the same. We have 7 planets in our system. So this was in 1584. We haven't yet discovered our Neptune, Uranus kind of places. All right. So then later, Huygens, who is actually way more popular for his weight, how the light propagates. Because initially Newton thought light is just a particle. It's kind of some particle like other particles. But Huygens was like the main proponent of the wave theory of light. That so like light is not like particles, but more like wave. So he actually wrote even a book on this, Cosmos, or conjectures concerning the planetary worlds, where he explored the idea of there could be planets out there, which is not part of our system.
There is a lot of echo.
By definition means
There is a lot of echo.
Like could be planets around other stars. When we see billion stars out there, all of them could have planets around them. But in spite of all of this, only in the last 30 years or so, humanity finally have the technology to actually do this as a science. Like it went from a field of philosophy to science. So many of you might have heard of this. The first exoplanets were actually discovered not around stars. They were discovered around something called pulsars. Are you familiar with pulsars? So these are basically really compact objects, like some tens of kilometers in radius, but they are almost as massive as way more massive than our sun is. But they're like really tiny, like size of half the size of Mumbai, but much more heavier than our sun. So these things actually rotate really fast and they send out like a beam of light, like kind of like a lighthouse. And as it rotates, you get like pulses. Every time that torchlight or that beam is towards Earth, we get a bright peak, right? And then it goes up. So you get these very periodic pulses. And these are called, that's why they are called pulses, because they literally appear as pulses when you look at space. And the way they discovered planets around pulsars is that these are very precise, they just appear exactly at the time. They're one of the most precise clocks in the world. So this is kind of what you can see what happens. So you have a pulsar here, and you get these periodic pulses of light from these stars, right? And if you study them carefully and observe them long, you will see in some planets, for example, in this particular case, ESR 1257 so you will see a lot of these numbers with many of the astronomy targets. They are just, that's how astronomers name things. Like now, we have a very systematic way of naming things, and that is how we end up with this thing. Let's stand here itself. So if you study them very carefully for a really long time, what they found was that some of the pulses arrived a little early. That that okay, the next pulse would come at this time, but it actually came a little earlier. And sometimes it came a bit late. So if you fit for that, you will see that okay, sometimes it came late and then early, and it sort of periodically went. So what this implies is that this pulsar is not standing there. It's actually moving away from you and coming towards you, right? So when the pulsar is coming towards you, it is closer to you. So the pulsar will come a bit earlier. When it's farther away from you, it is farther away from you. So it will take more time, right? So that is how they realize that the pulsar is not, but you see, it's not a stationary pulsar, but it is moving towards you and away from you, right? And what could make it do that? Like, in a space, when you have an object, right? If something is moving towards you and going away from you, that will only mean that it has some other companion which you cannot see. But this thing is going around the planet. And when two bodies in the space go around each other, from classical mechanics, that they don't go around they go around the common center of mass. So this common center of mass is far enough that this pulsar is slightly moving in the front and back, which is what you see as this oscillation from this pulses. Right? So that is how they discovered this. This is Alec Wolfgang and Ray Fay. So this was exciting. This was in year of 1992. Back then, exoplanet search was considered as a very exotic sideline subject in astronomy, because people thought, oh, we'll never be able to detect them. Nobody suspected they don't exist, but they thought we'll never be able to detect them. But this discovery showed that, oh, if planets can exist around pulsars, and pulsars, by the way, have a very violent history, right? You know how pulsars are formed? They were actually really massive stars. They underwent a supernova. And then the core of that star is what became pulsar, right? In spite of that violent history, the planet survived, which was around it, right? Or it could be that, okay, it captured the planet later, but that's a different possibility. But that is the exciting over what time scale we are discussing. This formation is so the pulsars are really high mass. They don't only have a few million years kind of a life, because they are really massive stars. So the life of a star is inversely proportional to the mass. Like, bigger the star is, smaller it be its life, because they will burn through their nuclear fuel pretty fast, which is hydrogen atom. Right? Unlike our star, which is not normal size planet. Okay, I shouldn't say normal. For us, it is normal. Sun is not the most common kind of star. There are actually something called M dwarf. I will quickly mention about it later, which is actually the most popular star in the universe. But our sun has 10 billion years, 10 billion years of life, right? Giga years. But these massive planets have a very tiny fraction of that, like 1/100th of the time of that to survive. So they are really. Oh, these pulses. Okay, so there are different kinds of pulsars. There are things called millisecond pulsars, where these pulses happen in milliseconds. And there are, the famous one is Crab Nebula, that's a 30 hertz, which means that you get 30 pulses inside 1 second. So there's a range, like, seconds to milliseconds. That's kind of the. Yes.
If pulsars are extremely massive, right? And the planet usually is not as compared to a star. We are Won't the compensation mass be extremely close to the center of the pulsar?
It is. It is.
Then you need to be extremely precise. Right?
Exactly. So that is what this method actually really excel, because these pulsars you get like in the millisecond pulsars, you get like 1,000 pulses in a second. So over a time, our atomic clocks have improved so much that we could very precisely measure these times to something like, the periods of many of these pulsars are known to something like 18 decimal points. So you know them very, very precisely. So this is a really exaggerated flow, right? What we're talking about is a really tiny shift, but they are detected. Yes, yeah, even lesser than that. But because you have a long observation, you can really get to that position.
Also, if the pulsar is shooting out like any sort of electromagnetic radiation, if a planet comes in front of it, the material is shooting out the radiation, we can measure that.
Okay,
Is
so
there a way we can use that to our advantage?
so far none of the pulsar, it's really, first of all, pulsar is not really pulsing. That's just what we say. It's kind of like a lighthouse. Lighthouse is not pulsing, right? It is constantly emitting radiation, but it is rotating, right? We see them as pulsars only because that is when that beam comes towards us. But from a pulsar's perspective, it is just constantly radiating on the side and it is rotating. So it is really unlikely, because that is also there's quite a lot of radiation coming out. Whether a planet will actually come, the probability of that is really small. Like, very likely the planet is in some other orbit, but the probability that it actually will interfere with that beam is, it's an interesting thing to calculate. But I should also mention, even though this was the first planets discovered, they are really rare. You don't find it around many pulsars, right? So that is one interesting thing in astronomy. Usually the first discoveries are always a rare exotic objects because they are easier to detect. And then as the technology improves, we find the actual number statistics.
So there are a couple of questions.
Yes.
Firstly, how does one differentiate between a quasar and a pulsar? And secondly, if a planet is within the Goldilocks zones of a pulsar, will it still be able to support life? If there is a life.
Okay, so first of all, quasar and pulsar. Quasar is a very different object. Quasars are from, at really far away galaxy, usually have a central black hole, which is sort of accreting stuff, and it's what is called anti-galactic nucleus. There's like so it's a very, it is massive, but not, it is way more massive than a pulsar is. Like if we are talking about billion solar mass kind of mass for quasars, and they are really, really far away, like really far out in the universe. But pulsars are nearby. They are in our own galaxy, and they are also in the nearby galaxies. And they are like more stellar mass, like something like 4 stellar mass. I mean, like much more lesser. I mean, it's a couple of stellar mass kind of pulsars. Yeah, what is the second question?
Second question was,
right.
if it is within the Goldilocks zone.
Yeah. So I will explain Goldilocks zone later in the talk for those who are not familiar with it. But it basically means when you're very close to the star, it's too hot, right? So the liquid water cannot exist. When you're very far away from the star, it is too cold. All the water is ice. Right? So there is a in-between Goldilocks zone where it's also called habitable zone. So the temperature is just right enough that liquid water can exist on the surface of the planet, which we think is an important feature for, at least the kind of bio life that we are familiar with. Now, so blazars, okay, so blazar and quasar are again in the black hole kind of thing. It's more to do with the angle at which you are looking at. So that is, it's more of an observational difference from the angle at which you are looking at it rather than. Okay, coming back to the habitable zone question. So pulsars have, we don't know what the habitable zone around a pulsar is to begin with, because they are emit extremely high energy radiation, like gamma rays and all those kind of things. So even if the temperature is okay, we suspect that it will be super highly irradiated by high energy photons. It's really hard to imagine a life form on the surface of these planets, because we don't know of any biomolecular reaction which will not get destroyed in a high energy radiation. right? So that is the question to that. But yes, theoretically, the Rex is a habitable zone, but not really habitable. Okay, let's go to the next one. This is actually the first exoplanet discovered around a sun-like star, like an actual star. Now, this is a discovery which won the Nobel Prize.
It's protein controls.
So yeah, this was just a year after the pulsar discovery. So, DQ, Michael Mayer, and all they have been looking for this for a really long time. They were like the pulsar discovery was a great moral boost to them because they know that okay, if people are able to find pulsars around planets around pulsars,
I don't see that option for the
oh, okay. It's okay. I don't think it's something important. Yeah. They were actually doing this by a technical radial velocity, which I will explain in a few minutes. But they were able to find this planet around 51 pegs. So this is the kind of, I'll explain again what this graph is and things like that. But this is like a really Jupiter, it's almost as big as our Jupiter. But it is super close to the star. It goes around its star in a 4-day walk. Even our Mercury takes 15 days to go around its star, right? So you can imagine how close this Jupiter-sized planet is to its host star. So these are called hot Jupiters. Because they are Jupiter-sized, but they are really hot because they are really close to the star. And these were the first ones to discover, again, because they were the easiest one to discover. This happened in 1994. Okay, and since then, as many of you might have heard, the history has been completely changed. Like we have now about 5,400 plus exoplanets discovered. So this plot over here shows how this has been changing over time. Like 1992 to 2023, you can see that we have been the cumulative number of exoplanets we have been discovered has been going up really steep. Like we have been making quite a lot of progress in discovering these planets. These different colors here, the red color here shows the planets discovered by radial velocity method, which I'll explain in the next minute. Then we see this green one. This is one which actually the radial velocity has been making constant, steady, and slow progress. And then you can see a huge spike in increase in the green color bars. These are because of transit method. And they are mostly thanks to 2 satellite missions. One is called the Kepler mission. It's a NASA mission, as well as the test satellite which is shown out here. So these are the 2 satellites which has contributed most of the green part of the discoveries. Okay, so how do we detect these exoplanets? The first one, which the green bar I talked about, the transit method, the idea is very simple. You just keep staring at n number of stars in any particular region, very precisely measure the brightness over time, right? And if you are lucky, right? If you are really lucky, the planet is in your line of sight. The orbit of the planet is in the line of sight at which you are looking at the star. Then once in a while, the planet will cross, occult or transit the star, right? So when it does, you get if this is a brightness over time, when the transit happens, it will get a dip over here. So you can see that if a big planet crosses over it, you get a larger dip in the brightness because it is blocking that much light. If it's a small planet, you get a smaller dip. So this method gives you the radius of the planet because the radius determines how much of the light it blocks, right? Pi r square is the area of the circle, and that tells you. And now this plot, I haven't put any actual noise or anything, so it looks like a clean signal, but this is a really hard signal to detect. But it is possible if you are observing it from space, because you don't have the atmosphere and all those things which is moving up here. Otherwise, the observation, right? You can really do preciseness. Now the next method, so this method gives you radius. Yeah.
Can a brown dwarf post like a star?
I'm sorry, can a brown dwarf?
Post exoplanets like a star or
Yes, it can. They are really, really hard to detect because many of these instruments we look in optical, right? So brown dwarf are more brighter in mid-infrared radars, right? We need to look at really mid-infrared radar. So the technologies that we have are not sufficient enough to very precisely detect it, but they will absolutely have planets around them too. Like Jupiter has moons around it, right? A brown dwarf is almost the same size as Jupiter, but at least 10 or more times more massive than Jupiter. But the size is almost same as Jupiter, and it can definitely have planets. So it's not. Whether you will call it a planet or a moon is a different question, but it can exist. But extremely hard to detect. The other method, so I said the first method gives you the radius. The other method is called radial velocity method. So here the idea is that, again, as explained earlier in case of pulsar, you have a star in the center and a planet. As they move around, the star, they rotate around in their common center of mass. This is of course highly exaggerated, as is pointed out. This point is actually very close to or inside the star, right? So this is a really exaggerated diagram, but basically it is still moving forward and backward. And we cannot see the planet. Just like in this case, we cannot see the planet. We are seeing the impact the planet has on the star. Here also we are seeing the impact this planet has on the star, right? Star itself we can observe because they are bright and they are sending you light, right? And if you look at the star, have you heard of spectrograph? So this is, if you take a prism, you might have done this in school, right? You take a prism, you send the light to it, you get all the rainbow colors out, right? And if you look very carefully, those spectrum will have certain absorption dark lines in it. Right? Those lines are because of absorption of certain wavelengths of light by the gas in the star. And that is what is depicted here. So this is kind of like the spectrum you get if you use similar to using a prism, but way more sophisticated than a prism, but idea is the same. You get these tiny absorption lines. And if the star is moving away from you and moving towards you, you can measure the position of these absorption lines very precisely, right? And if it is moving towards you, you get a blue shift to the photos, right? You have a Doppler effect. So what you see is the Doppler. When you have a light source moving towards you, it will appear blue shifted. Like that means if something is wavelength at some certain wavelength, it will appear more bluer than that. If it is moving away from you, it will appear red shifted. So that is what you try to measure here. And now this is measuring how much the center of how far away the star is moving around the center of the mass, right? Which means you will know the mass of the planet. Right? So this method gives you the mass of the planet. This method gives you the radius of the planet. And if you have mass and radius, then you can calculate the density, right? Because density is nothing but mass divided by volume. And once you know the density, then you can start talking about whether this planet is made of gas, just like our Jupiter, or it is a rocky Earth kind of planet. So density tells you that, like whether what kind of planet we are dealing with. And to detect both, only in a very few systems, out of 5,500, only a small fraction of them you can do both. Right? So even though we have discovered 5,500 planets plus, not all of them, all of the density we know, right? Some of the mass we know, some of the radius we know, but only in a small subset we know both of them. Okay, so then there are two other methods also, which I will not quickly, I will just quickly mention because they are also important. The other one is called gravitational lensing method. Here what happens is that you have a star planet, right, traveling in the sky, and in the background there is another star. So what happens is that when this planet star system goes in front of your background star, the gravitational potential of this, like Einstein general relativity, the gravitational potential, well, bends the light that is coming from this background star around that planet and focuses towards you. So you get a bright increase in the brightness. So as this planet star system moves across, you are sitting here and you have a background star. As this planet star system moves across, you will see the background star's brightness increasing. That is simply because of the fact that now more light is getting focused towards you by the potential of this planet, this star. Now, if there were no planets around this star, you will get a peak like this, and as the planet star goes away, it comes down. But if there's a planet around it, you get a micro lensing effect, which is like, a tiny blip as this goes through. Because the planet also focuses it. And this is very precise method. It's one of the most sensitive method to measure really small mass planets. You can measure easily up to Mercury-sized planets within this technique. One drawback, you measure it and this system just moves ahead and you will never ever be able to find it again. So it is like, they exist, that's it. Like, no follow-ups possible to understand more about those planets, unfortunately. But it's really good to know, statistical studies. And the other method is the direct imaging method. This is where for planets which are really far away from the star, you still can't see any light from the star. But if they are really far away, you have some instrument called coronagraph, which you block the light from the central star. It's like you're driving in a highway, there's a huge beam towards you, and you can't see anything else. That's what happens when you're trying to get the planets. But by an instrument called coronagraph, you block that bright star light, which is why it appears dark in the center over here. But then you have these tiny peaks coming up. These are planets. So this is a famous system which has been, in the time, I don't know, you can see there is a timestamp there, which is increasing by 2012, 2013, 2014. It's many years of observation, and you can see these planets. So these are really great because this is one method where you're directly seeing the planets, which is also useful. Okay, so that is the overview of how we detect these planets. And each of these methods have its strengths and weaknesses, which has resulted in us in populating this plot. So this is what is shown is how far on the x-axis here is how far the planet is from the star. And on the y-axis is the mass of the planet. So you can see that different methods which are shown by different colors. Transit methods, we have higher probability of detecting them of these planets are very close to the star. Radial velocity method also similar, but you can, there's more leeway around that. Imaging method, you can only detect they are really far away from the star. That's why they are all clustered over this corner, right top corner. And the micro lensing, as I was saying, is one of the most sensitive methods, which can really push it down here. One thing you will notice is that the Venus Earth anode is also shown over here. We still haven't reached the technology precision level where we can detect Earth-like planet around sun-like stars. That is still far away, but not very far. We might reach there pretty soon, but we're getting pretty close. This thing has been coming down, down, down. You can see that we are discovering things very close to it. So that's kind of really nice.
Yeah, slightly different question.
Yes.
Are there any examples of something revolving around the black hole?
Well, our entire galaxy is revolving around a black hole. But yeah, black holes go around black holes itself. That's what LIGO has been discovering with all the
Actually, very specific. Are there no
planets around black holes? No, none so far. Mainly because how do you detect them? Like, we usually detect most of these planets by detecting the host star's properties. If the black hole is moving back and forth, the only thing you will know it is moving back and forth is from the gravitational waves. But the gravitational wave astronomy has only begun. Maybe some decades down the line we'll have enough precision to do that.
So it's perhaps as of this moment, no. But
as of this moment, nothing discussed. It definitely could be. Yeah, that's
In the radial velocity network, what if it's not like simple system, right? The radial velocity, you have only one planet. What if you have several planets that are floating around, say, a sun or a star or whatever? In that case, the star will be the entire system will have a center of mass, which is different. And when you calculate using the method that you mentioned, you will get say, on a combined planet, right?
No. So there is this, are you familiar with the Fourier transform? It's a very beautiful technique. So what you measure is how the star is moving back and forth. If there are different planets, there are dynamics presets, and these planets cannot exist in the same orbit. Right? It's like in our solar system, there will be a different orbits.
Like gravitational talk about these two planets coming here, each will have its own brand effect. Why is that one of the reasons why we would not always be the same?
Yeah, so it's a stability reason. Like each other one will make the other planet unstable. Like it moves down. There has been, I think, for a long time, before Maxwell proved this cannot happen, people suspected about something called Planet X. That is that there could be another Earth which is on the other side of our Earth orbit, but we never see it because it's always behind the sun. As we go around the sun, the thing comes across. But then it was Maxwell, I believe, who proved that no, that cannot exist because that is an unstable point. The planet will either get pushed far outside or inside, so it will not remain in the same orbit. So, yeah.
An exoplanet around popular star,
Popular stars of constellation.
like we could figure.
There are many stars around constellations. Off the top of the head,
There is pockets.
Pollux, yes. Pollux B is correct. Yeah, there are many. See, every star out there are planets around it, right? It's just whether they are detectable because of the angle orientation. Coming back to the question, it's a very important question about how you detect when there are multiple planets. Each of these planets will have different periods, like around the star. Periodicity. Exactly, right. And
But what if the mass and radius ratio is the same, that orbit will be different.
Huh.
The ratio line is same. One thing Newton's law, which I will be able to do in this case.
yes,
The gravitational is not too much. Then-
no. So even if the mass is same or mass ratio is the same, the period is different, right? Because if the planet is closer, it will be rotating at a certain Kepler period. If it is farther out, it will be a different period. So the amplitude of the shift will be the same if the mass ratio is the same, but the mass radius ratio is the same. But the period will be very different. Like for example, Jupiter will cause a 12-year period in the sun's radius. If some alien is looking at our sun, Earth will cause a 1-year variation. Jupiter will cause a 12-year variation.
It's just like theoretically not possible to have the same period, or is it practically very less probable?
It is theoretically not possible to have the same period. They will not be stable. Like you cannot have same period means they are the same orbit. Right. Which is okay. Now it is possible, kind of like a planet moon system, like or a planet and another system in the Lagrange points. Okay. The only thing in our solar system which can go at the same period as our Earth, which is not on the Earth's orbit, are the Lagrange point objects. Like Earth has L1, L2, L3, right? They are usually, if they cannot be as big as our Earth, because then that means that they will have other things going on between them. But we can have tiny moons which goes around. But any massive planet similar in size has to be necessarily going around at a different period. So then you will see what you get is a sum of all these different periodicities, and then you take a Fourier transform which selects the period at different frequencies. Then okay, this is at this period, and this is, you can basically decompose your radiation into different for over several observations. Exactly. Yeah. All of this requires a lot of observations over time to decompose them. Okay. Now that I've given an overview of how we discover these planets, and we have discovered so many, we can do statistics with it. Like, we no longer have to study one planet at a time to understand things. We can look at the overall things. One very popular thing people do is look at their occurrence rate. Like, this is called a demographic study. Okay. The name demography is a misnomer. It has nothing to do with humans. It has to do with planets, but we still call it demographics of planets. What we have discovered is that the number of kind of planets out there is not uniform. What is shown by this plot over here on the x-axis is the size of the planet, and I put these different planets from our own solar system so that you get a feel of what I'm talking about. And on y-axis is the number of planets per star. That shows you how frequent these kinds of planets are around other stars. And this, of course, only complete for 100-day orbit. So we are talking about planets which are within the 100-day orbit. So what you will see is that the Jupiter-like big planets are not that common. I mean, it's there, like at least not inside 100-day orbit, it is not that common. Saturn also is more popular. Neptune, as it gets smaller, the number of planets in the universe is also increasing. They are getting more and more popular around other stars, which sort of makes sense, right? To make a big planet, it's harder from the planet formation perspective. It's easier to make smaller and smaller planets. So this kind of goes up, and one of the most common planet is around what we call sub-Neptune, or some people call it super Earth. That's like a fuzzy boundary. Unfortunately, our solar system does not have a single one. Right? So we don't know, but they are the most popular planets out there. Unfortunately, our solar system does not have a single one of them. Then something interesting happened. Then there is a drop in the number of planets which are around 1.8 radius of our Earth, right? And then again it comes back up. And Earth is over here, and Earth's number is somewhere. It's still hard to estimate, because we don't have that enough sensitivity. But we expect, every out of every 100 stars, there has to exist about 8 Earth-like planets. So now the biggest question, this is called radius value. Why is there a dearth of planet at around 1.8 radius of our Earth? Why is there much less planets out there? So one possibility is something called photo evaporation, right? So what could be happening is that the planets are, some of the Neptune-sized planets are getting evaporated, and they are becoming small, right? This is just a hypothesis. We'll go into more detail to explore this hypothesis. Is that the reason why you see lesser planets? So we'll go into that. And so what causes the planets to evaporate? As you all know, stars emit light in all the different wavelengths. So, and different stars emit different amount of light in different wavelengths, right? So what is shown here is what astronomers call a spectrum. So this is the same thing as you see when you put a prism in the sun, you get different lights. So you can see the red color, the reddish part over here, and the bluish part over here, the rainbow spectrum color thing. But if we actually very precisely measure, I told you there'll be some places where there's a number of photons coming at that wavelength, right? So that is what causes these dips. And these are what astronomers call absorption depths, right? Now, these are tiny dips because some molecule or atom in the surface of the star is absorbing that photons. So they are not reaching you. Right? So depending on what wavelength. And then the important thing is that this is only a tiny part of the entire spectrum in which the sun emits, right? We can only see from 4,000 angstrom to 7,000 angstrom, around that range, what we call the bench or rainbow colors. But there are a lot of photons emitted which are much shorter in wavelength, and shorter wavelength means higher in energy, which is called the ultraviolet regime. And if you go even further, you have X-rays, which we humans know how to create on Earth. Gamma rays too, that's like really crazy things. Not much gamma rays from a normal star. Gamma rays usually happen in quasars and all those high energy stuff, but not from a star. So very little flux in these regions, but it is there. So for our sunlight star, most of the light is emitted in this optical region where we see, right? It's not a coincidence because we evolved on the Earth under sunlight emission. So it makes sense to have eyes which are sensitive in the wavelength where our sun emits the maximum. And then there's infrared, radio, everything further down, right? Okay, now, does all of these photons does not contribute to heating a planet? Like, for example, what happens if you shine optical light? If you have a torch, light from this tube light, it is coming out mostly in the optical wavelength. It usually gets scattered by something and bounces around and goes away, right? So that is pretty much what happens to the most of the optical light from the star. Like when the star emits optical light, it gets scattered by the surface or by the gas in the planet, and they just goes back into the space. Most of them, some fraction of them will get absorbed, but most of them just ends up going back. But now that is not true if you are talking about much more shorter wave, like ultraviolet radiation, right? Why? Because most of these gas giant planets are made of hydrogen and helium, right? And atoms only absorb at a certain set of wavelengths, right? They don't absorb all the wavelengths of the light. Right? If you have extreme UV radiation, which is wavelengths less than 500 Armstrong, that is a UV part. They will basically end up absorbing, like the electrons in the hydrogen will absorb that photon and escape the atom. Right? So what you have is what is called a thermal electron. So XUV radiation, which is unlike the optical one I talked about earlier, will get absorbed by a hydrogen atom in the atmosphere, and it will become an H plus without an electron and an free electron. And this free electron will have the kinetic energy which came from this photon energy, and it will randomly bump into everything else around it, right? So it will transfer that whatever the original photon energy into heat. Because heat is nothing but random collisions and vibrations, right? So this is very efficient mechanism, right? Unlike optical light, which just gets mostly scattered away, when you have UV plus X-ray radiation falling on a planet, they will get almost immediately absorbed by the planet and gets converted into heating. So it's kind of like a radiation-driven heating of the planet. So that is what happens, and this ends up significantly heating the planet. And what happens when you heat a gas? So, and many of you might remember this from school. There's something called Maxwell-Boltzmann distribution. This is if you have a box of gas and they have a certain temperature, what is the velocity of the particle? Right? There will be some particles which are just really not moving around. Some particle will be buzzing around your box, and some particle will have an average velocity. And what is the distribution of the velocity of that atom or molecule of that gas inside your box is what is given by the Maxwell-Boltzmann distribution. And that is what is shown over here in this plot. So on the x-axis here is the speed of the particle, right? And on the y-axis is the how common that speed is. So what happens in this system is that when you have a really cold gas, like 200 Kelvin, so that 200 Kelvin means about minus 80 degrees Celsius. Like if you have a dry ice kind of chamber, like the dry ice that you get when you buy ice creams, the gas will have a typical velocities of something around 1 kilometer per second. I know you have realized this, like that is the typical velocity of the gas molecules inside a bomb. So next time when you get a dry ice box, it looks like, oh, it's just gas, but actual molecules are moving really fast inside, right? So you'll have about a kilometer per second speed for most of the gas. But not many gas will have velocities more than 2.5 kilometer per second, right? They will be still small. But if you heat things up to such a room temperature, like this room, 300 Kelvin, right now the molecules here, okay, we are not 300, but around 300. The average velocities are slightly more than 1,200, around 1,200 kilometer per second, right? So that is the velocity at which the molecules are zipping past us right now, right? They're really tiny, lucky for us. Otherwise, it would have been like bullets all over you and hitting. So they are really tiny. So that's why they can move at these speeds. But that is the velocity at which they are moving. Like that's really fast. And there's a reason why somebody opens a perfume bottle somewhere and those molecules are really heavy. Still immediately you get the smell, right? So that is really fast. Or like oxygen level in the atmosphere is so uniform, right? Like if it weren't for that much fast transport, these small openings would not have been sufficient to balance the oxygen between you and the outside region and all this kind of thing, right? It was really important to us. Otherwise, we will be all, as humans come together, suddenly there will be a dip in oxygen. That does not happen because of this fast exchange of velocities. And these velocities are non-intuitively fast. Now, the interesting thing happens when you heat this gas, right, to faster and faster things. The average velocity of the particles increase, right? But also, more interestingly, the fastest velocity the particles can reach also increases significantly high. By the time you are at 2000 Kelvin or 500 Kelvin, you already have many particles which are like more than 4.5 kilometer per second, right? And that one goes really, really fast. And now what happens when you have a small fraction of particles which can go really fast? We all know about the escape velocity of our Earth, right? So if you have a particle, yes. So, okay, escape velocity is the speed at which you should be going to escape the gravitational potential of a planet or a star, whatever, right? So if we have, a small velocity planet, they will just go up, even if they randomly end up going in the up direction, and they will slowly lose their kinetic energy to potential energy and then come down, right? But if you have greater than escape velocity, you can escape outside the potential of the planet. Right? It's kind of like this animation shown over here. So this is kind of the way the molecules in our atmospheres are. At the sea level, like where we are in Mumbai, you will have the maximum number of molecule density. Like our Earth's atmosphere pressure is really high. As you go up, the number of molecules are lesser and lesser. Like by the time you are at Himalayas, 4,500, it will really hit you. You realize that there's lesser oxygen. And by the time you are at Mount Everest height, that is above 8 kilometers, but for the death zone, because people die, there's not enough atmosphere pressure there. Above 8 kilometers, and if you keep going up, the number of density is less. But still, there will be always some molecules which have enough velocity, which can come really high and escape our Earth. And how do you quantify this? Like, how do you know what is the temperature where this number of molecules escaping the potential of the planet is large enough? So that you can do by, I just put the equation there, but you don't have to worry about it. But what we define a quantity, which is just the ratio of the gravitational potential. This is how much gravitational potential it should escape, divided by the average thermal energy, right? So you can imagine if this ratio is, this ratio will be always, has to be greater than 1, then most of the particles will remain, right? But if this ratio becomes really large, like for example, the gravitational potential is really large. This is the case when what is called bound system. That gravitational potential is 30 times larger than the average velocity of the molecules. You only have a tiny fraction of molecules escaping it. There's still non-zero amount of molecules escaping in a planet, system. But this is a really tiny fraction. So this is what that fraction is what is shown in this plot. So the x-axis here is the velocity, and the y-axis is the fraction of molecules with that particular speed. So this is called a bound system. So for all practical purposes, we say that planet is not evaporating. Right? The planet is mostly as it is. Not much molecules or atmosphere are escaping that planet. But now, as either the thermal energy increases or the gravitational potential decreases, for a planet, usually it is always thermal energy increasing because you're heating it, right? When you heat it, your thermal energy increases. You enter a regime called Jeans regime, where you have even more number of particles escaping. Then you enter a regime called boil-off, and then there's a regime called blow-off. This is like a really. So this is when that ratio is only 4 times that. So the gravitational potential is only 4 times larger than the thermal energy, which means a significant fraction of molecules. Even though the average energy is still not sufficient to escape, a significant fraction of molecules can escape. And now this results in an interesting scenario, just like a Mumbai local train. You have some molecules which have enough energy to escape. But because of the collision, some others also get dragged along with it. Right? So that is exactly what happens in this system when you're in a boil-off scenario, right? You have these few high energetic particles which will take the entire crowd along with them, right? Because if you have one particle just hanging around, some high velocity particle will come and hit it, and because of the collision, that particle will also go in that same direction. So you go. So it's almost becomes a regime of fluid flow. So it is there's this regime of random molecules escaping, and then once it becomes dense enough, you have something, a property which is similar to a flow of fluids, because they all flow in a very high density environment, and all the fluid flow equations can be used to calculate those systems. So that is the scenario, and this results in something called Parker wind. So Parker first proposed this for sun like stars, like how stars have winds. We all know our sun has something called solar wind, right? Which is the sort of gas coming out. The question was, how on earth is that happening? Because sun is really massive. How are these gases escaping the sun? And what is driving this wind? Like there's no fan on the surface which is pushing them out, right? Something is driving this wind out, and this is the mechanism, right? It becomes really hot. There's always a small fraction of molecules which can escape the potential, and they drag with them everybody else. Right? Again, you can ignore all these things here, but basically what this shows is that you get a velocity field. What is shown on the x-axis is the height as the gas moves away from the planet, and the y-axis is the speed at which they go. The important point is that at one point they will be going faster than the speed of sound, right? And speed of sound is important because speed of sound is the speed at which any pressure in the atmosphere propagates, right? After all, the sound wave from my mouth is just pressure modulations, right? Which is reaching your eardrums. If something is moving faster than the speed of sound, they cannot make a pressure on something which is farther away, because before your pressure because of some gas reaches that point, that pack of molecule itself will reach that point. Right? So this kind of results in a situation where nothing here can influence something back there. Like once they are cross the sound speed, they just go circle. Right now they cannot influence the gas behind. Right. And this is a very simple mechanism. Like the temperature of the planet determines the velocity at which this fluid flow happens. This wind flows out, or the planet is evaporating out, and the amount of mass which is escaping determines the density of that wind. Right, two parameters which are very important when you have to actually observe these things. Okay, how much time I have? Oh, 10 minutes. Oh, okay. I will skip this part other than just quickly to mention that the amount of gas that will escape a planet, or how fast you can evaporate a planet, depends on the amount of radiation that is falling on it and inversely proportional to the density of the planet, right? The density is important because that determines whether the planet can be evaporated or not, right? If the planet has a low density, you can evaporate it much easier because the gravitational potential is less. But if the planet is very dense, it becomes very high dense, so you cannot evaporate it very easily. And this has been used to explain the radius value, right? The plot I showed you much earlier, right? Why there is a dearth of planets at about 1.8 radius of the Earth. And that is what, yes.
That's the type. We talk about that also
Sorry, time.
Time.
Yeah.
The rock mechanics. How is it impact the rock mechanics? How is it impact the patient's plan?
Exactly. Right. So precisely that is what that matters. Because density is whether it is rocky or gas determines the density, right? So Jupiter is much less dense than our Earth because it is mostly gas, and it's much bigger than us, right? So what happens is, this is on this plot shown over here. This is where even if you start with massive planets, like really massive planets, if they are like 10 times the Earth mass kind of thing, that is not like Jupiter or more, you will see that they are big enough and strong enough that they still have enough density that they can hold on to the gas. They will not get evaporated away that fast, right? However, if you have a planet which is something like 6 Earth mass, Neptune, less than a Neptune size, they are not dense enough to hold on to their hydrogen, helium gas, right? They don't have that much gravitational potential. So if you have a star which is irradiating a lot of XUV radiation, they will evaporate, and over time, even if the radius was originally up here, they will drop down to just the core. So once they reach the core, which is the this silicon kind of mantle structure, then there is no much hydrogen helium to evaporate. So then they will become stable at that particular radius. So this is the density over here, 5.5 gram per centimeter cube, which is kind of like the density of the material here.
That they become stable.
Yeah.
All right. So what are the other factors also? Probably these two factors will be stable.
Stability in terms of evaporation. So this stability is sort of like a false stability in the sense that there's nothing left to evaporate as a volatile, right? So that is why it is not hot enough that it will evaporate magma or anything that way, but it will evaporate all the gas like hydrogen, helium, which planets, like when a planet forms, 99% is just hydrogen, helium stuff, right? The rest of it is just small, tiny fraction. Right? So all of that stuff will get evaporated away, and you will be left with just that the iron and all those heavy metals in the core, and that is where it sort of reaches that. No, so sputtering happens in a later stage. With yes, sputtering can cause the like meteorite kind of stuff to kick out things and make it escape the potential, but they are a much tiny fraction. But what we're talking about is just literally evaporation. Like this is the irradiation. It's like you have a heat gun. You're shining at the planet, and the planet is just hydrogen, helium is just getting evaporated away from the planet, which is different from throwing a metal, some material, sputtering and forcing them. Yes.
So, due to radiation from the sun, can it happen that the radiation acts as a catalyst for any chemical reaction with the gases? Hence, the gas, when the gas reaction does not have to be the contact of gas. Several elements may react to form much heavier gas. And when your density of the then it probably reaches the critical point of will not be able to evaporate.
Yeah, so definitely photo driven react, like even in our own ozone getting dissociated and things like that, right? So but they are usually those things happen for much more rarer elements like oxygen and all. From perspective of hydrogen and helium, yes, hydrogen, it's very hard to get them locked up in other molecules because their number is so much higher. Like the universe has 90% of hydrogen and helium. Like in case of our Jupiter,
And they're quite light.
yeah, they are very light. It's really hard for them to, because even if every every oxygen molecule combines with hydrogen to form water, the number of oxygen you started with is so small, it does not make much decrease in the number of hydrogen atoms because it's a tiny fraction only, because there's after all 2 hydrogen can become water only if there is 1 oxygen. They're always limited by the oxygen, right? So even if we have a lot of hydrogen, so hydrogen number perspective, it doesn't really change much. But yes, there can be small changes in the numbers because of the photochemical reactions.
So evaporation can happen at a certain amount of gas.
Yes. Yeah.
And that is part of the time which is not evaporate, that is shifted in equation.
Yes, and that we believe is what happened on Earth, for example, right? How did Earth end up with nitrogen dominated atmosphere? Like we don't have much hydrogen and helium on Earth.
Yeah.
So we lost all of our primordial atmosphere, and then things degassed from the surface. We formed this secondary atmosphere with a lot more complex chemistry because it's not just boring hydrogen and helium, but all this other molecules. So yes, absolutely, that's very valid. But again, from all exoplanet perspective, it is a tiny fraction. Like if you look at the Earth image, like Earth is, if you consider Earth as a ball, like the atmosphere is a tiny layer on it, right? Which is from exoplanet perspective is like basically a rock with a tiny bit of a layer on top. But that's not the case for Jupiter and all, right? Jupiter is mostly atmosphere, right? So that's, yeah. So from observation perspective, Earth is a rocky planet, not an atmosphere with planet. But there is an attempt to detect this. So this is how end up. So when we end up with this, what happens is that most of the planets here get blown away, the atmosphere gets blown away, and they end up being this smaller super kind of planets. They pile up here. So, yeah.
So your phenomenon takes into another point that is magical. So now this particular time for just for understanding, imagine the field of right? The star has ready to start and it's that. But I think see there is a wrong it has a because of their gravity, the force now remains here or the possibility of plasma in this.
So you're thinking about a rocky planet.
I'm just thinking,
Okay.
you're something that we can handle.
Yeah, right. Okay, so did I understand? But the question is like if you have a gas, like for example Earth, like can they get evaporated? That-
To be done.
To be evaporated. Yeah.
Now, what you retain, what you are retaining with is the again,
Yeah.
right? So, do you have sufficient gravity force itself hold on to the element? Or do you think last long and first?
So in most situations, they will have sufficient, but not always. Like for example, Mars, like it is small enough that even though there are a lot of degassing happening from it, it could have had an atmosphere much more than what it currently has. But because of it has no extra protection from the magnetic field like Earth has, their atmosphere keeps getting stripped out all the time when the sun goes into anything, right? So it's a very, at that point, it becomes, we're talking about small numbers, but for that small planet with only a tiny fraction of atmosphere, it's a big thing. Like, if it gets a tiny fraction of absorption, could completely deplete it out of that. But even then, Mars has an atmosphere, right? It's not as much as Earth has, but it has. So there is that balancing which will be very specific. On the other hand, Mercury is like completely blown out. Like even it has a tiny atmosphere, but very very like, almost yeah. Okay, so that's how you end up all the planets which are here gets evaporated and then end up on this pile up here. Right. So that's how you get a pile up on this side. That's one way of explaining what we see. Why there's a dearth of planets at around 1.5 radius. Now, this is all good, theoretically makes nice sense. Exactly, right? So far I said all theoretical possibility. Have we actually tried to observe this and actually validate this? How do you do it? Right? How do you try to observe? So there is this method called transmission spectroscopy. Right? What we try to do is that we try to wait for this planet to do the transit in front of it. And if you imagine a planet 4 can be this black thing and it can have an atmosphere which is shown over here. This of course highly exaggerated, right? Depending on the system, it can be a really tiny thing. And what we want to measure is if it is evaporating, we should see this extended and outflowing, right? Now, how will you actually detect for them? And how does the whole transmission spectroscopy work? We again use the principle of spectroscopy. What happens is that a star will emit all kinds of wavelengths of radiation, right? Short wavelengths, long wavelengths in between. And many wavelengths, if it is a very short wavelength, they usually get scattered away by an atmosphere. Like it's kind of like the blue sky phenomenon, right? Why do we have blue sky? They get scattered away and they come out all that way. Other wavelengths, some of the wavelengths they just pass through because there's nothing absorbing that particular wavelength. But there will be certain wavelengths which correspond to certain electron transitions in the molecules in the atmosphere, which will cause them to get absorbed. For example, this wavelength over here, you can see it got absorbed by this particular molecule is stopped there, this yellow over here, right? So certain wavelengths will get absorbed more in that atmosphere, while other wavelengths will pass through. So when you're looking at it, you will see the amount of absorption from the planet depends on the wavelength at which you're looking. Right? Because if it is this particular yellow wavelength that you're looking at, you will see that there will be bigger absorption because of the atmosphere. But if you're looking at this red wavelength over here, it is something passing through, so it will only be broke by whatever is the core of that planet, not the atmosphere. Yes.
So, the light in the star itself is limited by the probe.
By the most of the light we see comes from the atmosphere, what you call the photosphere of the planet,
Yeah, so it's
of the star.
around the star. And the star, assuming in this case, it's not a very massive star and it has mainly. In that case, light itself is going to pass through layers of the atmosphere of the star.
Yes.
And a lot of it is already by the stars and the hydrogen is going to absorb few of the spectral lines.
Yes.
Now when it passes through the planet, to any exoplanet, and if the planet itself has hydrogen and helium in the atmosphere, like how do we get to know the difference they observe? Because is it the sun that absorbs, is it the star that absorbs it, or is it the planet? How much?
Right. Excellent question. So what we do is, how do we repeat the question? Oh, for the okay. The question was, we see a certain absorption line, and as I was also mentioning earlier, these absorption lines are coming from the gas in the atmosphere of the star, right? Now, if we see an extra absorption because of planet, how do you know it is not an absorption in the star itself, but from the planet? The trick that astronomers do is that you take the spectra of the star when we know the planet is not in front of the star, right? So that is called the baseline spectrum, right? Then you again take a spectrum when the planet comes in front of the star, right? So you have two spectra. This is called in-transit spectrum and out-of-transit spectrum. Then you divide one from the other, right? So if there was an excess absorption by the planet absorption, it shows up as the deeper thing. So you take a spectra of the star when the planet is in front of it, spectra of the star when it is not in front of it, and take the ratio, right? So that is the idea. Yes, it is much easier because the planet transit only for a tiny fraction of the time. So you need to know exactly when it happens. Most of the time it's not that. So you just take a step. And when it is, and you need to know when the transit is happening. So you have to know that precise, which is done first with other photometric telescopes. Then you predict that okay, this planet is going to transit, keep your spectrograph ready. As soon as it transits, you take the spectrum. So that is how it is.
So after each rotation, we should get lesser and lesser.
No, they don't. Even though I said evaporate, those evaporations I'm talking about are in million-year time scale. So from our last 5 years of technology, you don't see any difference. You will see same difference.
What is the angle that you're seeing it with? Ultimately, from your perspective,
I suggest we hold on to the questions for the time being. Let it come.
Okay, let's finish because then we can discuss.
We can keep this.
Okay, so this is how the spectrum, transmission spectrum looks, and this is what you will see if you are looking Earth from, if you are an alien, like you are looking at Earth when Earth is transiting. You will see this sort of absorption because of molecular oxygen, ozone, etc. Water absorption because Earth atmosphere has water. You have methane absorption, ozone absorption, carbon dioxide absorption, all this kind of absorption, right? Which will tell you, okay, there are all these molecules in the Earth atmosphere. And this is a theoretical spectrum. By the way, Chandrayaan-3 actually has a spectrograph on the orbiter, which is called SHAPE, which is looking at Earth. Just like we will look other planets around it. So, Earth as an exoplanet is one of the missions. And you will actually see the spectrum of the Earth. So, which will match this. So far, nobody has been able to see this. This is a theoretical calculation. And Chandrayaan-3 will provide that observation. Okay. Now, how do we detect this absorption? As we are discussing, we want to look at some absorption, some wavelength, which there has to be enough strong absorption because the signal is very faint. The strongest signal out there is hydrogen because hydrogen is the most common gas, and the wavelength at which hydrogen absorbs the most is the Lyman alpha wavelength, right? So this is the transition from the ground state of the electron to the next higher level. Right, so this is a Lyman alpha. This is in UV, ultraviolet wave. Yes. Unfortunately, it's an ultraviolet wavelength, which means you have to go to space to see it because Earth's atmosphere will absorb out it. And this is how the first evaporating atmospheres were discovered. There you can see this is again a spectrum. You see this black curve over here. Actually, first see the dash curve. So this is the out of transit spectrum, and black curve is when the transit is there's a planet in front of it. And if you look carefully, you see that this black curve is below this dash curve over here. Right. So that is the first signal that people detected, which said, oh, there is an absorption. And you also see another big problem here that the center there's a huge dip here. That is because it's not this planet which has hydrogen. Our entire interstellar medium is full of neutral hydrogen, right? So they will also absorb. So you don't actually get the core wavelength signal. They are just absorbed by the interstellar medium. Only those, because planet is moving at a very higher velocity, right? You could actually, because they are redshifted than the interstellar medium hydrogen, you can actually detect it. But even though this is the most sensitive way of detecting the atmosphere, it is not very efficient to get the full picture, because you only get the highest velocity absorption molecules in this exosphere, not the core. And again, it's expensive because you need Hubble Space Telescope to do this observation. You have to be in the space. And yeah, as I was saying earlier, the geoprobe. So there's a new probe which has come up, which has become quite popular in the last 4 or 5 years. Is use helium. So helium is the next most common element. If you ionize helium, they reach something called metastable state. Like an atom you can ionize, they become excited, and then you recombine. They combine in some higher energy levels, and they come down to a lower energy level. Right? And 75% of the time, when a helium recombines with this lost electron, forming back a normal helium, it comes into something called a metastable state helium, right? And that state can absorb photons at 1083 Armstrong, which is in near infrared. The nice thing about it is that it has a very high probability of absorbing, so it's very sensitive. But the best part is that the interstellar medium does not contain any ionized helium, which means if you detect something, that has to be coming to either from the star itself or from the planet which has been irradiated by here. Also, our Earth's atmosphere does not contain any ionized helium, which means you don't have to go to space to do this observation. You can do it by sitting on the ground with large telescope. On the ground, we have this huge telescope. Right? So what do we need for that? We need big telescope for that, right? This is one such telescope. This is a 10-meter telescope in Mobile, Berkeley, where we built an instrument for. And to get an idea how big this telescope is, if you are a human, you will be only this big. Like you see this thing there? So that is the height of a person. Okay. And this is a huge telescope. This diameter of the telescope is about 11 meters in size. Right? And this, once you have that much collecting area, then you pass it into a high resolution spectrogram, which is called the Habitable Sort Planet Finder. And you try to observe this spectrum in transit and out of transit. So meanwhile, usually just to give you an idea of how the science thing works, this is a case where the theory was proposed first and then the observation happened, right? Sometimes in astronomy, it happens other way around. Somebody observes it, discovers something, and then theory comes next, right? This is a case somebody proposed that, hey, this is possible to detect. Please go and look, right? And people looked at it immediately. So even the theory paper came out in 2018, end of 2018 itself, we had observation levels. So this was actually done from the space because the data already existed, and they were able to see an excess absorption at where the theory predicted it to happen. And since then, people have observed this. So by the way, these plots are, as I said, in transit spectrum divided by out of transit spectrum. So any increase you see here corresponds to an excess absorption at this wavelength, 10,830. This is where that medium exists. So this is the first detected. And again, just to give how it usually plays out in science arena, not everything is well constrained in theory. Like one of the biggest input is how much radiation is there to ionize helium. Unfortunately, we cannot observe and measure that from the star because our interstellar medium neutral hydrogen will absorb that. So the only for sun and some nearby stars, we have an estimate of how much XUV radiation is emitted by the star. All the other stars, we just have a model. Right? So we have a theoretical model of understanding. So we make some calculations and we predict, okay, this star might ionize. If this planet is evaporating, it might ionize. And then we go for it. So one of the first theoretical prediction was for a star called GJ436b. We observed it and we know it has an evaporating atmosphere, but we did not detect, right, with lot of. But but you don't give up. You keep looking at different stars and you finally find the one. This was like one of the first discovery of a evaporating atmosphere around an M2 star planet kind of things. Okay, and this is just another example from a very recent work where it's a HAD P32 system. This planet has an evaporating atmosphere so big that it has filled up its orbit with the gas coming out of it. It's almost 51 times the size of the planet itself. So it's like the longest structure that has been seen from a planet. By the way, this is not an image. This is again a modeling based on the absorption signal that you have got. So we can sort of do some fluid dynamics modeling and recreate what it might be to actually look up close in the system. You can see that there's this planet undergoing evaporation and they are basically filling up the gas. Okay, so we are really running out of time. Just give a quick overview of the things. The plot here shows kind of the summary of what I've been talking about so far. Different mass of planets might all be formed. When they form, they all have 90% hydrogen, 10% helium, whatever that high fraction is, right? You can have big Jupiter-like planets, some maybe left with just embryos, just silicon kind of parts. But then over time, as the system evolves, right, Jupiters will still hold on to their gas because they are massive enough. They will still have the hydrogen helium gas, and they will be end up with just like in our own solar system. We see them mostly hydrogen and then helium, and rest of it is a tiny fraction. Right, but for all of these planets, which are the most common in the universe, unfortunately, our solar system does not have an example. They will lose all of their hydrogen, the primordial atmosphere, which is mostly hydrogen helium. Right, they will all be evaporated away, and they will be left with just the core. And once they have the core, then that core will slowly degas from really complex atmospheres like our Earth's atmosphere with nitrogen, helium, and all. Which is look at, for example, a comparison. Our on Earth, Venus, etc. If we look, very different composition. Like we hardly have any hydrogen in our atmosphere. It's mostly nitrogen, oxygen, argon, and so on and so forth. Because they are all secondary atmospheres which came later, right? Not the primordial gas which formed the planet itself, unlike our giants. That is how we understand the current planets that we see. All right, I think I'll stop here.
So we'll take an online question. We'll stop the live stream, take a tea break, and then people here can ask. Sure. Okay. So the question now is there any model which can predict how much time Earth has? In a way. Or any planet.
Yes, so Earth has been studied pretty well because it's pretty important, and even before exoplanet field, geologists have been studying the thing for a long time. So I myself am not an expert on the Earth's thing, but the idea is that at least for a million-year time scale, as the sun's brightness increases, our temperatures of the Earth will start increasing. So sun itself has a 5 giga years left, that is 5 billion years left, but Earth does not have that much time because in a few million years, the sun will become slightly bigger, which is hot enough to start evaporating the water in our Earth seas, and you end up with a runaway greenhouse effect where, because all the water vapor, as we know, is one of the carbon dioxide we are struggling already. Once the water starts evaporating, it is even worse because you have a huge runaway greenhouse effect which will end up evaporating all liquid water on the surface of Earth, and they will hang around there. They will not get evaporated away as long as our magnetic fields are there to protect our tiny atmosphere. But it gets really hot and probably very hard. But exact time scale other than a million year, I don't know that.
So the speaker should be content, right? Yes, so on this note, we'll end the live stream. We'll take the tea break and then we can resume the.
Thank you. Thanks for again.
So we can end with
Again.